Okay, hello. We're going to continue talking today about convolution of distributions. All right. So last time we eventually got to defining convolution or convolvable pairs of distributions, and when a pair is convolvable, what the convolution is. So today what I want to do is talk about examples of convolvable pairs. Okay, so this is a project that's a bit like what we did when we talked about normal convolution. We talked about pairs. L1 gives you a convolution in L1, and LP LQ gives you a convolution in LR, and these kinds of results. Well, we're not going to have analogs of those kinds of things for convolution of distribution. So the treatment is different in that sense, but we're going to start by thinking about convolutions with test signals. Okay, so we'll start with phi in D. Okay, and theta in D prime. Okay, so a test signal and a distribution. Okay, this may not seem like a enormously interesting convolution to define right off the bat, but we'll see that indeed it is, and convolution with things in here, it provides us, as we'll see, with a very powerful tool for in what's called approximation theory. So you have some class of signals which may have some properties that you may or may not like that much, but you want to approximate signals in that class with nicer things, and you don't get much nicer than that. In fact, it's a space of signals. These are too nice because they're so nice there aren't very many of them around. Okay, but nonetheless they do provide a rich enough class that we can approximate other things with them. Okay, and convolution provides a device for doing that. All right, so this is kind of moving us slowly in that direction. Okay, so what do we know in this case? So so let me write first. Let me abuse notation and write this instead of this. Okay. So theta is a distribution, theta sub phi, because phi is a local integrable function. This is also a distribution, but instead let me write that. Okay. So first, let's adopt that bit of notation, and then what's true here is, first of all, that this symbol always makes sense. So as a distribution, this is convolvable. Okay, and so again, theta is a distribution, and when I write this, I really mean this distribution. So we're gonna identify this function with this distribution. Okay, so it's convolvable, and the convolution corresponds to a C infinity function. Okay, so what I mean by that is that this convolution exists, and as a convolution of distributions, all we know is that it's the convolution of it is that it's a distribution. Sorry, but what this is saying is that it's a particular distribution, very special kind of distribution. It's a distribution which is the sorry, maybe let me cut to the chase and actually just very clearly write down what I mean. So, i.e., there exists an f in C infinity R f such that phi star theta is theta f. Okay, so that's what I mean. And lots of other things are true. Okay, so it's an infinitely differentiable function, and so you can ask what are its derivatives. See, so what's the kth derivative? Well, it turns out that you can apply the derivative in the convolution to either component in the convolution. So this can be, oops, that's not what I wanted. Okay, so it can be phi k star theta, and it's also phi star theta k. Okay, and so this always makes sense. All right, this is an infinitely differentiable function, so I can differentiate it certainly k times. This is an infinitely differentiable function, so I can differentiate it k times. And distributions are always, you know, in the appropriate sense, infinitely differentiable. Okay. All right. So there's a class of convolvable distributions. Okay, now let's look at another set of convolvable pairs. All right, so if rho is a distribution with compact support. Okay, so we talked about these last time. So this was the set of distributions corresponding to the test signals in E, and the test signals here were just infinitely differentiable functions on all of R. And the topology was the topology of uniform convergence of the functions and all of their derivatives on compact subsets. Okay, so rho is in there, and theta. And so I hinted at this last time and kind of didn't say it as well as I might like. This when I was talking about the convolvability of the Dirac distribution with any other distribution. So let me try to say it better this time. Okay, then, whoops, theta rho is convolvable. Okay. Okay, so why is that the case? Okay, so remember how we defined the convolution. So the convolution was defined by taking the tensor product with the way that we had this function of this distribution in two variables, and so the way we did this was we took tau star phi. Okay. So this was a test function in a single variable, and then we defined a test function in two variables, which we called tau star phi, which was phi of t plus s. Okay, and then we multiplied this by some test function in two variables. We took a sequence of those that converged to one and as a special approximate unit. We took the limit as j goes to infinity. Okay, and this was how we defined the convolution of theta and rho. Okay, and so I tried to say this last time, and I'll try to do that again. The point here is that when I define the tensor product acting on this thing, okay, because rho has compact support, okay, I can choose j here large enough that it's 1 on the support of rho, okay, and in which case then this is for large enough j, okay, this is going to be theta applied to, and then we had this thing phi rho, capital phi rho phi, okay. And remember how we defined this, okay? So this was defined by fixing one of the variables in this function of two variables. And so really, if I'm going to use the notation that I had last time, this should really be tau star phi, okay? And the reason that I get to do this is because rho has compact support. And so again, what I've done is I've taken j large enough, so this is 1 on the support of rho, and then this operation of constructing phi from rho, and this infinitely differentiable, but not necessarily with compact support function, makes sense, okay? Because I can multiply by any function with compact support, which is 1 on the support of rho, okay? And so the point is this thing is in here, okay? All right, so we argued that last time in the case where we had an arbitrary test function in two variables here. And so we had this thing had compact support, but now what we're doing is we're transferring the support condition to rho, okay, which has compact support. And so this thing still has compact support, okay? So it's infinitely differentiable with compact support. Right. And so, the point is there's a trade-off here. You have to have some support conditions. You can put the support condition on phi or on rho. And in this case, we're putting it on rho. Okay. All right, so that's how convolution with something in E prime works. All right, so you can always convolve things with distributions with compact support, and this is sort of one of the classical cases that people talk about. With a distribution theory is distribution with compact support, and one of the reasons that it's interesting is just that that includes the Dirac distribution. Okay. Okay. So one also has continuity of these operations. Okay. Oh, so maybe we mentioned this last time, and I'll just sort of mention it here again. That if theta and rho are in then so this means the support is bounded on the left, okay? Then this is convolvable. And the convolution also has support bounded on the left. Okay. Now, When we talked about convolution of functions, we talked about continuity, right? So I think my policy in this is that. Okay, and so, when we had the convolvable pair of, say, L1 with L1 that mapped into an L1, there was a continuity condition which was given by a certain norm bound for the convolution mapping here. Okay, now, so distributions, the convolution of distributions also has continuity properties like this. You do have to be a little bit careful here, because they're not quite exactly the same as they are with spaces of signals. Because with spaces of signals, we had very strong continuity properties. We basically gave norm estimates that were of the form of f star g in some norm was less than or equal to something like this, right? And so you had continuity of the bilinear mapping of convolution. Okay, in convolution of distributions, you generally don't have continuity of that bilinear mapping, and that's because the spaces of distributions have topologies that are just a little bit that you have to be more careful with than you do with norm and semi-norm, the kinds of norms and semi-norms that we were talking about with convolutions of functions. Okay, but what you do have is you have continuity in each variable with the other one fixed. Okay, so for example, here, if you fix theta, then it's continuous in phi, and if you fix phi, then it's continuous in theta. Okay. All right, so in all of the above cases, we have a certain type of continuity. Okay, namely, not mainly, but namely, if theta rho is convolvable, then the mapping theta goes to theta star rho is continuous. Okay, for each row. Okay, and where we use the so there is an issue here of topologies even that you have to be a little bit more careful about than you normally do, but we won't maybe get into it too deeply. So the topology we use for, let's say, theta here. Okay, and so theta in each of these cases, so in the first case here, theta is actually phi. Okay, and phi is in here, and so we use the topology on D. Okay, here theta is in D prime. Okay, so we use the topology of D prime, the weak topology of D prime, and then similarly here theta is in D prime plus, and we use the weak topology of D prime plus. Okay, so we use the topology the topologies of so I'm going to refer here to these three cases as 1, 2, and 3. Okay, topology of D in 1, okay, of d prime in in 2 and of d prime plus 3. Okay, and similarly, we have continuity of rho goes to theta star rho for each theta. Okay, with the suitable topologies. Okay, so that, just to be clear, in case 1, so rho was the role of rho was played by theta here, so theta was in d prime. Here rho is in e prime, and here rho is in d prime plus. Okay, so those are the topologies that I'm talking about. Okay, so let me just say with the suitable topologies. All right. Okay. So that's kind of the analog for distributions of some of the things we talked about for convolvable pairs of functions. Okay. All right, now let's talk about periodic convolution. Okay, and to talk about periodic convolution first, we need to talk about periodic distributions. Okay, so we're going to talk about periodic distributions. Okay, so we talked about periodic signals. Right, and there's also periodic distributions. Now, there's 2 ways to think about periodic distributions. One way is that they are distributions that are periodic. Okay. The other way is to define them kind of separately as their own class of distributions with its own class of test functions, and define continuity and take continuous duals and the usual thing you do to define distributions. So let's make the definition in the latter sense, and then indicate how it's connected to the other way of thinking about things. Okay. All right, so let's denote by, so let's let T be a positive real number and denote by D per T the set of T periodic infinitely differentiable Okay, so this is the periodic analog of D. All right. Okay, so that's fine. And so, for example, included in this pile of things would be, the harmonic functions. So in the complex case, it would be e to the 2 pi I n t over t for n, an integer. And then for, in the real case, it would be cosine and sine of 2 pi n t over t sine 2 pi t over t. Okay, so this is a particular collection of things in d per t. Okay, and these are called harmonic signals. And they're going to be very important to us when we talk about things Fourier. Okay, but that gives you a list of a list of familiar things in DPER. Okay, but there's lots of other things, and when we come to talk about Fourier series, we'll see a nice recipe for building large collections of things in here that are not of this form. Okay. Good. So this is our class of test signals, and as always, we need to define a topology on here, and we do this in the usual way by defining convergent sequences. All right. So a sequence psi j. So I'm going to be working with both dper and d here. So let me write things in dper as psi, and I'll reserve for phi things in d. Okay, so a sequence psi j in d per t r f converges to phi okay, okay, so remember the convergence in D had this condition of there being a common compact support for all of, not a common compact support, but all of the supports were contained in a common compact set for all terms in the sequence, okay? Well, you're not gonna have that here because, you know, these things don't have compact support, of course, but you know, in some sense, they kind of do have compact support as a result of their T periodicity, because all we really need to know one of these functions is we need to know it on the compact interval, say 0 to t. Okay, and so that condition can be dispensed with, and you just then ask for uniform convergence of the phi. I want psi here, not phi, of the psi j's, uniform convergence of the psi j's and all of their derivatives to psi. Okay. And so, and you know, really, again, this is defined on the compact interval 0t, and so, you know, uniform limits of continuous functions are continuous and all that stuff. Okay. All right. So in any case, if psi j k converges uniformly to psi k for all k's. All right, so the uniform convergence here is on all of R, but as I have been repetitiously saying, that really just amounts to uniform convergence on 0t. All right, now all right, so as I've already said, the harmonic signals are examples in here. Okay, there's another way of building these things. So if phi is a normal test signal, so infinitely differentiable with compact support, then define the periodization. Okay, and I'll call the periodization is going to be something which plays a very interesting role in Fourier stuff. So here's a first appearance of the notion of periodization. Okay, so this is going to be a T periodic test signal. And the way you do this is you just take the signal phi, and then, and so this is evaluated at t, okay, and then you translate it by integer multiples of the period. Okay, so if your phi looks like that, okay, then you just take translates of it. Okay, you add them all together. And because these things have compact support, there's no issues here with this sum converging, because for each t, the sum is guaranteed to be finite, just because you translate this for a large enough, sufficiently many multiples of the period, then you'll no longer intersect the support of phi, and so the sum will be finite. Okay. Okay. So then, so that's one way of building these things. Okay, and among the set of all things like this, okay, all periodic t-periodic infinitely differentiable signals, among all of them of this form are a certain important class. So we're going to denote by ut of our f the set of phis in D for which per the periodization of phi is equal to the function 1. Okay, so it's not really very super clear that there exist any signals like this. Okay, but the idea is that when you so it's t there, and t and 2t, that when you it's going to have to look something like this, right? Okay, so that when you add their values at any point, they add up to 1. Okay, so my drawing isn't very good, but that's the idea. And so proving the existence of one of these, you have to fiddle a little bit with your with functions of this form that we've looked at before, that are infinitely differentiable with compact support. Right, so there's some fiddling around you have to do, but you can do that. Right, so this is a meaningful collection of test signals. Right. Okay. Good. So then so there's our examples. Okay, now once you have your test signals and their convergence in that space of test signals, then the definition of the corresponding class of distributions is just that it's the continuous dual. Okay, so then a periodic distribution is a continuous linear map on theta from d per t into F in the usual way, okay? And we're going to denote by, obviously, d prime per t, the space of periodic distributions. Okay. All right. Okay, so what's the connection between periodic distributions and distributions that are periodic? Okay. Fact, theta is in d prime per t of r f, okay. Okay, so here, let me try to say this more carefully. All right, so let theta be a distribution, an ordinary distribution. Then there's, because you have to be careful how you connect a periodic distribution with a distribution, because they're inherently different things. Something in here takes a test signal in D, and something in here takes a test signal that's periodic, and so it's not clear how you make a connection between something in here and something in here. So we should be clear how we do that. All right, so okay, so now as a distribution, the first of my three equivalent statements is that theta is a t-periodic distribution. And what I mean by that exactly is that tau t star theta is equal to theta, okay? So we defined this shift operation on distributions, okay? And this just says when you shift a distribution by the period t, you return back to itself. Right? So this is exactly analogous to periodic signals. If you shift it by the period, then you leave the thing alone. Okay, so that's the first statement. Okay. Now, the second statement is there exists a unique theta tilde, which is a periodic distribution in the sense that I've defined, such that, okay, so this is where you need to connect the fact that theta takes an argument from D, and theta tilde takes an argument from D per T, okay? So how do you do that, right? Okay, such that, so you need to take a periodic test signal and convert it into something in D. And the way you do that is you multiply by one of these things in UT. Okay. Such that for any, let's call it mu in UT RF. Okay, so remember that this is in D. All right. Okay, such that for any such mu, we have, okay, theta tilde of psi. All right, so my convention is that psi's are periodic, and this is going to be equal to theta applied to mu psi. Okay, and this is true for every periodic psi. All right. Okay, so this is how you connect the fact that theta tilde and theta have different arguments, is that you take the periodic argument of this periodic distribution theta tilde and you turn it into a normal test signal by multiplying by one of these particular test signals with compact support, namely one whose periodization is 1. Okay. And then finally, let me express this same kind of condition, but in a different way. Okay, sort of more or less making reference to periodization. Okay, there exists a unique theta tilde again, periodic. Such that okay, theta of phi, okay, is equal to theta tilde of per t of phi, okay, for every phi in D. Okay, and so here the connection goes the other way. All right, so what I did here was I started with a test signal that was periodic. Okay, and so that is a natural argument for phi tilde. Right, and then I indicated how you convert this thing into a normal test signal so that you can give it to the normal distribution theta. Okay, and here we're going the other way. So we start with a normal test signal with compact support, and then we convert that into something which serves as a test signal for the periodic distribution theta tilde. Okay, so conditions 2 and 3 kind of go give us both connections between distributions that are t-periodic and periodic distributions. And so fortunately, those things are the same. Okay. All right. All right. So let's look at convolution of periodic distributions. Okay. All right. Okay, so so the definition here is a little bit tedious. You have to do it slightly differently than you did for the regular convolution, right? But here's how it goes. Okay. All right. So so I have, first of all, let's denote by these two mappings. All right, and they're the obvious projections onto the components of R2. Okay. And for F, any function from R to F, we're going to use this star notation that we've used before. We're going to denote by PR1 R1 star F of, so this is going to be now a function of two variables, S and T, is going to be F of PR1 of S and t, which is f of s. Okay, and similarly, PR2 star f of s and t is f of t. Okay, so just gives us a way of converting functions of one variable into functions of two variable, because we're going to use the tensor product of distributions, just like we did to define the convolution for ordinary distributions. All right. Okay. All right, so here's how you define the convolution. All right, so let theta and rho be periodic distributions. All right. Okay, so define their convolution. Okay, so this is the periodic convolution. All right. Right, by. Okay, so I need to tell you what theta convolved with rho does to a periodic test signal psi. All right. Okay, so what you do is you use a definition that's so let me write it down, and then I'll try to explain where it comes from. Okay. All right, so there's the definition. Okay, so let's see if we can make sense of this. All right, now remember what the usual construction was of convolution. So we certainly had this kind of a thing, right? So we have this periodic test, and so I should say here psi is per t. Okay, all right, so so we had this kind of construction also for a convolution of distributions. It's just instead of a periodic test signal psi, we had an ordinary test signal phi, but this is the same thing, right? This is psi of t plus s, all right? All right, and then we had to kind of, in order to apply the tensor product to the argument here, in the regular case, because t star tau star phi did not have compact support, okay, what we had to do was we had to multiply it by a test signal with compact support of two variables, okay? And we're doing something similar here, okay? We're taking, we're trying to create a test signal with two variables, but we have to at the same time account for periodicity, okay? And so what we're doing here is we're really making use of this formula up here that we use to relate a distribution, which was t periodic, with a periodic distribution. All right, so we took the periodic test signal psi and we multiplied it by one of these right, so u here was in this class of test signals whose periodization was 1. Okay, and here we're essentially doing that in both variables. Okay, so we have this test signal, which will be now a periodic test signal in two variables, okay, s and t. And then we're multiplying it by these test signals like here, which will convert this as a periodic infinitely differentiable signal into one which has compact support by multiplying it by these guys. All right. All right, so the idea is connected to what we did to define the normal convolution of distributions, but there's a few differences here. In the normal case, where we have this thing, in the normal case, what we did was we had a sequence of these, and then we took the limit. Here, things are easier. And remember, when in the normal case we had this sequence psi j, and these psi j's had the property that as j got large, these became one on larger and larger sets. So I asked you to think about balls that whose radius grew to infinity as being this, as defining the sequence of psi j's here. Well, because I'm working on with t periodic things, okay, really I'm only working on the interval 0t, so I don't have to worry about taking that sequence of balls that grows to infinity. It's already going to work on the compact subset of R2 given by 0t cross 0t, right? So that's kind of what's going on here. And one of the consequences of this is that sorry, sneeze. One of the consequences of this is that periodic distributions are always convolvable. Okay, so without any conditions. And it's really because they bear more resemblance to distributions with compact support because of by virtue of their periodicity. Okay. Okay, and there's a not exactly completely trivial thing to show that that this is indeed t periodic. Okay. But you can do that. All right. Another fact, and again, this has to be true, or else the definition of convolution isn't very useful. And that is that if f, g are in L1 per t. Okay, so this is kind of the big class of signals whose convolution you can normally take as just as functions. Okay. Then, so we know in L1 per that any two signals in L1 per are periodically convolvable. So that's also true when we convert them to distributions. And of course, the convolution of the distributions is the distribution of the convolutions. Okay. Okay, good. All right, so I think that's all that I want to say about convolution in terms of general constructions for classes of distributions and classes of signals. What I will do next time is I'll give some important results that have to do with approximation theory. So I talked a little tiny bit about that today. And so maybe next time we'll do that in a sort of careful way about approximating signals in certain classes with signals that are have much stronger properties. And so we'll see exactly how that goes next time.